Alright, solving more complex trig equations is the topic for this video. We're going to be looking in more depth at different types of trig equations. Okay, remember trig equations are equations that have, for instance, sine of x equals to 1/2. That would be an equation. We usually solve this on a certain range, and our most common range is where the input, I've used x here, but you've seen this as theta, is usually between 0 and 2 pi. Okay, now this could change. Okay, if this was from 0 to 3 pi, I would need to find all the answers from 0 to 3 pi where the statement is true. Okay, so we're going to look at more instances like this, but where they're a little bit more complex. Okay, and there's basically three types. The first type is trig equations that are quadratic in form, that look like this. Okay, we have trig equations that require identities, that will require me to switch certain expressions for more simple expressions. Okay, and we'll do two of those examples. And then the third type is solving trig equations that are so complex, right, that you can't solve them algebraically. So you'd have to use a calculator, and you would do this by graphing. Okay, so if you can if you had access to your calculator, then you would probably need to solve this type of question by graphing, and we'll look at an example like that. Alright, let's start with the first one that involves a quadratic form. Okay, so here we have a trig equation. You can see right away I have a 2 times sine squared, so that's a squared term, so that's why we call it quadratic. 2 sine squared theta minus 3 sine theta plus 1 equals 0. Let's solve this. So we need to find the angles theta, the values of theta between this in this domain, such that this statement is true. If you look closely at this, this looks a lot like a regular quadratic equation where we're just solving for x, right? The only difference is instead of x, I now have a sine of theta. So just so that you don't get too confused with this, let's review a little bit on solving quadratics. We have 2x squared minus 3x plus 1. We can factor this, and we end up with 2x and x here. That's 1, so that would be 1. That's a minus. So if you can see right away these two would work. This would be, and since that's a plus, it would have to be minus and minus. Okay. So the solutions to this would be, okay, obviously if it said solve, x would be equal to 1/2, or x would be equal to 1. So here I have two solutions, right? My solution set would be 1/2 and 1. Likewise, we're going to do that, except we have the extra step of having like a sine function here, or a cosine, or some trig function here, and then it just becomes what we did in the previous section with solving for that angle on this given range. Okay? So let's go ahead and solve this. This looks very similar to this, so it'll be 2. Okay, I'll have a 2 there, I'll have a 1 here, and I'll have a 1 here and a 1 here, right? 2 times 1 plus 1 would be 3, okay? So, and since that's minus, we'd have a minus in here. Okay, well, what would go in here? Since our variable, kind of our chunk here, is a sine, we just write 2 sine theta here, and here this just becomes sine of theta. Okay, so this is now equal to 0. This is the same statement. We now solve for this, so we end up with sine of theta is equal to 1/2, or sine of theta is equal to 1. And now we have two situations, or two problems that are very similar to what we've done in the previous section. Okay, and so if we solve both of these, we get on the interval from 0 to 2 pi, okay, theta will be pi over 6, 5 pi over 6, right, for this guy, and then for one revolution of sine theta, we get theta equals pi over 2, right? And that makes sense because if you look at your unit circle, okay, sine of theta is equal to 1 right here, okay, at 0, 1, and sine of theta is 1/2 at the angles Okay, that would be 1/2, right, when that's 30 degrees and that's 30 degrees, which is these two angles. All right, so I think that's pretty straightforward. I guess my final solution set then would be this, this, and this, so you could write just the three of them in order. Okay, so if you write it as a set, that's fine. Okay, all right, let's take a look at the next example. Whoops. The next example is solving trig equations that involve identities. Okay, sometimes we'll get now if you look at this question, you can see that I have two trig functions. Okay, so oftentimes I want to get it in terms of one trig equation so that I can solve it, or get it in a factored form with one side equal to 0. Okay, so that I can factor the other side and use the zero product property. Okay, this is called the zero product property, where we factor one side and then we can solve each of those individually, find out where they equal to 0. Okay, so we're going to do that same process here. Well, let's look at this. I have a cosine of theta here. I have a sine squared over here. Well, maybe if I can write everything in terms of cosines, it'll make my life easier, right? Because then I'd have, since I have this sine squared theta, if I can convert this into an expression that has cosine squared, then I would have a similar situation to what I did in example 1. Okay, well, what relationship do I know about sine squared theta? I know that sine squared theta plus cosine squared theta is 1, so I know that sine squared theta is equal to 1 minus cosine squared theta. So maybe if I can substitute this, it'll simplify my problem for me. So let's try that. 3 cosine of theta plus 3 is equal to 2 times 1 minus cosine squared theta. Okay, and now if I expand this and then move everything to one side, maybe I'll get that quadratic. So let's try that. 3 cos theta plus 3 is equal to 2 minus 2 cosine squared theta. Okay, so that looks pretty good. Let's move everything to one side. If I move this over here, that becomes positive 2 cosine squared theta. Okay, that stays the same, plus 3 cosine theta. Move minus 2, so that becomes plus 1 equals 0. Okay, now let's see if can I factor this. And it looks like I'll be able to do that. This factors out into, okay, well, that obviously is going to be 1. That's going to be 2, and I'm going to have 2 cos theta and cos theta. Since that's positive and that's positive, that's got to be plus 1, plus 1. So I can now split this into two problems. Since this side, if this is 0, then this statement is true. If this is 0, this statement is true. That's called the zero product property, right? So let's set this equal to 0. If I do 2 cosine of theta plus 1 is equal to 0, or cosine theta plus 1 is equal to 0, and solve each of these, then whatever answers I get from my angles will make this true. So cosine of theta will be minus 1/2, and here I have cosine of theta equal to -1. All right, and if I look at my unit circle here, at what location is the cosine -1/2? I have a -1/2 here. That's going to be my x value, so it's going to be at these two locations, right? So theta is cosine is -1/2 at 2/3, right? That's going to be a 60 degrees. So that would be cosine of theta, or theta would be 2 pi over 3 and 4 pi over 3, because that's what this angle is. Here theta would be equal to, if I draw it over here, okay, -1's over here, so that would be at pi. Okay, that angle would be pi. So my solution set then would be from 2 pi over 3, 4 pi over 3, and pi. Okay, so that would be my solution set. All right, notice I'm going from 0 to 2 pi, okay, because these answers are in the interval 0 to 2 pi, okay, where this is not included and this is included. That was just one of the conditions that was given to me at the beginning.